So I'd like to invite our next speaker, Professor Daniel Goldman from Georgia Tech, who runs the CRAB lab in complex rheology and biomechanics. Daniel, are you okay to start sharing your screen? And we can go from there and see what you and Rebecca discussed and how they aligned. Oh, we can't hear you yet. Do you need to be unmuted? Yes. Is there any chance we could unmute Daniel, please? Let's see if I can do it. I should be able to do that.
Hello, hello.
You should be unmuted now. Perfect. Excellent. We can see your screen. We can see you. I will hand the presentation over to you.
Okay. Well, thanks. Am I coming through okay?
Yep, loud and clear.
Okay. Well, my name is Dan Goldman. I'm a physicist. And I'm going to talk to you today about novel environmental interactions during aerodynamic self-propulsion via self-deformation, which is a whole lot of fancy words, which I'll try to explain. And like Rebecca said, we had a little chat before this workshop, and I was very nervous to present because I had no idea what embodied intelligence means, although thanks to Rebecca, I feel a little more sanguine now. But then I looked at a nice, review article by these folks, one of whom, or maybe several of whom are represented here. And I learned that embodied intelligence is the computational approach to design and understanding of intelligent behavior in embodied and situated agents through consideration of the strict coupling between the agent and its environment, situatedness, mediated by the constraints of the agent's own body, perceptual and motor system, and brain embodiment. And at first, I got a little sad because I saw the word computational, and I'm an experimental physicist. That's a thing. And I said, what am I really now? I don't know what embodiment is, nor intelligence, nor computation. I don't do much of. But then I saw the word environment, and that made me happy because environment is what my group in the last 14 years here at Georgia Tech has spent a whole lot of time working on. And I'm going to tell you just one little story today, which I hope will get you excited about the possibilities for interaction with the environment. And it has to do with organisms and robots interacting with complex, heterogeneous terrestrial environments. Okay, these are the folks who've done it. I'm just going to flash these up because I know these will be recorded and people can gaze upon them later, but you know, I'm just the messenger here. Okay, so I'd say our best self-propelling devices, and I mean self-propulsion where the system itself is generating all the thrust and we're not steering them around with magnets or with whatever other external force. That's our best self-propelling systems are those which function well in relatively homogeneous environments. These could be aquatic, aerial, paved roads. I hope you can see my mouse. And I would also say that interestingly, they self-propel or locomote without much self-deformation. So basically they work largely by spewing, as I tell my classical mechanics class, which I'm teaching now, spewing stuff out their backsides, and those reaction forces by Newton's third law push them forward. Well, okay, those are the kind of environments our best technology works in. I would say our best technologies does not yet work at with the same level and capabilities in terrestrial environments. And when I first entered this business, I thought, well, terrestrial environment means paved roads and flat ground, and we're sort of done. But I've come to realize that terrestrial environments are actually terribly complicated, ridiculously complicated, including things like Martian soil, built environments, which I don't have a picture of. I have unbuilt environments here. This is a sidewalk outside my building, as well as natural environments like leaf litter and forest terrain and snow and grass. And the interesting thing is that we're interested to discover new principles of what we're calling aerodynamic interaction to better understand animal behavior and improve robot task, locomotion performance, and active matter more broadly. What do I mean by aerodynamic interaction? Why do I need a term like that? Well, this has come up as we've started to think about how organisms and robots interact with this diverse, incredibly complicated terrain. I don't know if this video will play, but it's one of my favorite videos where you can see some of the players, or at least cousins of the players in my lab we like to study, moving using diverse changes in body shape, self-deformation, over this complex, nasty terrain, which can be rugose, it can be flowable, it can have cliffs. Sometimes even this little a lizard like this has to even squeeze through confined and constricted environments. And it turns out that these are problems are a wonderful source of novel pterodynamic interactions with limbs and bodies with complex terrestrial environments. Okay, well, I just want to make a plug for my former student, Chen Li, who runs the Pterodynamics Lab at Johns Hopkins. And if you're interested, you can check out all the cool stuff he's doing. In my group, we've taken a comparative approach. Ever since I was a kid, I loved critters, and I guess I'm now recapitulating my childhood as a faculty member. And so we're interested not only in how individual organisms and increasingly robot models of those organisms move in complex environments, we like to take a comparative approach to see if there are common principles across such diverse organisms. Sometimes there are, sometimes there aren't. I'm going to tell you one thing today, which I think is actually we've looked into, which seems pretty generic, and that's a story about a little snake called a shovel-nosed snake. It'll only take a few minutes. This is a snake we've been studying for some years. It's a champion sand swimmer. It lives in the desert southwest of the United States, where its environment is largely homogeneous sand, but on the surface there are these sort of sparse brushes, heterogeneities. This is a cool animal because indeed it not only swims within the sand for distance, but at night it comes out to forage. And when it forages, you could see a path. This is a picture taken by Perrin Schiebel, one of the PhD students who've worked on these animals. It executes this beautiful sinuous track across the environment. And one of the cool things here is that this is a kind of complex terrestrial environment, which is complex in the sense that it's made of sand and heterogeneities, but not that complex that the environment is changing at every footstep or snake bend. Basically, you have flat or dry sand with some hills plus some heterogeneities. So we got interested in the problem of what does this snake do? We had studied what it does beneath the surface. What does it do when it's zooming across the surface? If you're interested in how it zooms across the surface, you could check out this recent eLife paper when it encounters these obstacles. And the cool thing here is that we had previously discovered this snake is almost like a robot. Unlike the snakes that live in your garden, which display actually rather complicated shape changes over time, this snake basically plays a wave on its body, and it looks very snaky from head to tail, and that's what propels it well. It turns out that's adaptive for moving on sand. Okay, well, we did a physicist version of a desert. We put an array of posts here, which is our sparse heterogeneities. You can sort of see them here. And then we just chased a snake hundreds of times through this array of posts just to see what would happen. I should say the snakes don't see very well, okay? And they tend to move really fast, and they tend to like to play this wave. And here's what happens. After 182 experiments with 9 snakes and tens of undergrads chasing these for summers, we find this map. This is a sort of probability map where the black is the midline of the snake over lots of different snakes. Okay, it sort of looks like a mess. But if you look more carefully at sort of rings, annuli of where you might find this snake, near enough before the scattering, you basically get a distribution of probability where it's essentially peaked where we started the snakes off. Further away, from post lattice, you get kind of a mush of probability. And as you go further and further away, this mush separates out into a multi-peak distribution, which basically says that when snakes come out of the lattice, they either go straight, they diverge off to the right a little bit, the right a little more, the left a little bit, the left a little more, in kind of discrete units. Okay. And if you've ever taken any physics classes or waves classes, then you will say to yourself, boy, that looks a whole lot like diffraction of waves, and we call it mechanical diffraction. But I just want to make sure that you understand this is not quantum-like diffraction. However, it's not unique to these snakes. We got interested to see how robust this effect is. So we tested this in a more controlled model, a robophysical limbless robot, where we basically have a bunch of serially connected motors, which we can program to generate a sinuous pattern of undulation. And the game is, we wanted to mimic something about the snake. We wanted to keep this open loop. We wanted to make sure that the robot hits, and it's only mechanics. It's only the interesting pterodynamic interactions which might cause changes in dynamics. So we did that, and this is what you get. You start the snake robot at various initial positions. By the way, it's got wheels on it, so it's coupled to the environment, so it can generate a low slip movement. Sometimes it goes left. Oops, well, I'm not showing you where sometimes it goes right, but here's some data where you could see trajectories off to the left, trajectories off to the right, depending on initial conditions. And if you do this hundreds of times, this time a graduate student picking up the snake robot, putting it down, here's what you get. I'm just going to build up these probability maps. And you get sometimes the snake, this is its head, This is its body. Sometimes the robot goes straight, sometimes it goes off to the left, sometimes it goes off to the right. If you compute the probability distribution of scattering angle, you find that basically, indeed, it's kind of this peaky, discretized distribution. Cool. But one thing I loved about this is so cool is my physics forebears in the early 20th century have all sorts of great statements because they didn't know about robots or active systems, that both matter and radiation possess a remarkable duality of characters. They sometimes exhibit the properties of waves and other times those of particles. Now it is obvious that a thing cannot be the form of wave motion composed of particles at the same time. The concepts are too different. Well, how different are they? Well, I claim that active systems which self-propel be a self-deformation of the kind that Rebecca was just narrating so beautifully, and the kind we've heard about throughout the workshop, naturally mix wave and particle aspects, and this principle can be used to develop control heuristics and even maybe better robots. And in fact, one of the interesting aspects of this is that there's sort of an uncertainty principle for these kind of robots, where if I try to, this is a plot of basically how spread this probability distribution is for scattering as a function of the spacing between the posts. As I squeeze down those posts and try to localize that robot, it responds just mechanically, aerodynamically interacting via scattering more strongly. Okay. And by the way, the curve fits Fraunhofer diffraction. I'm using it. No idea why. Okay. Here's the one use for this stuff. You can develop what we'll call anticipatory control active scattering framework. It turns out, through a long story, which I won't tell you, but you can read the paper, that the scattering angle is dominated by the head collision duration. And so based on that idea, we used an amplitude modulation method from these folks, and we put a little contact sensor on the head, and we were able to, and this is now we have an automated gantry, which you can see sort of following along. When it's just open loop, it scatters strongly. But when you apply a controller, which basically knows, depending on what side of the head it's going to hit on, which way it might scatter, knows something about its diffraction pattern, you can basically reduce the spread of this distribution and make the snake robot go through the lattice very simply without a whole lot of trouble. Okay, one last little example. We got interested then to take this idea and see if we could use it to see what's going on in the snake's brain, or in the neuromechanical control scheme is what we call it. So we then slowed down the videos of our snakes colliding, and you find all sorts of amusing things, like because they're moving fast and because they don't see, when they hit obstacles, the body basically buckles strongly. And after some time, then they reorient and go on their way. And in fact, this is kind of funny because, as you might know, a whole lot of money in physics goes into physicists throwing things at other things, colliding things, and using the remnants of the collision to understand the microscopics of what's going on inside the system. So we're using these scattering experiments to let us peer into the microscopics. And it turns out that one key fact about snakes, which you might know or might not know, but the folks who build snake robots tend not to, is that snakes aren't serially actuated robots. Snakes are largely, you have a vertebral column, and then you have tendon and muscle arrayed on either side of the vertebral column. And Bruce Jane figured out in the late 80s that basically snakes play a wave of muscle activation, which activates and stops activating and activates and propagates down the body. And on the contralateral side, that muscle is off. So it turns out that you can then make a model, which Perrin did, which we call the play and buckle model. You play the wave down the body, and you assume that at points where the muscle goes from active to inactive are preferred buckling points. See the paper if you're interested. But it turns out that that model reproduces the experiment beautifully. And so in some sense, the robot's body and wave, body properties and wave are doing some, I guess you'd call it morphological computation to allow it to squirt through that lattice in a much better way than our animals. Okay, where do we go from here? Well, we got inspired by this, and a team led by an undergrad decided, well, all the robots we know of are serially connected, motor on motor on motor. Why not try to model some aspects of the snake? And so we think we've created a new kind of robot here, which is basically a spinal cord and motors, which wind up little gears, which then pull in an analogous way to the snake's interaction pattern on either side of the body and can generate this nice locomotion. It has the cool passive property that it's easily bent towards active motors, but difficult to bend away. And it turns out that when you put it in a collide against a wall, like the snake, it kind of reorients spontaneously. The cooler thing, though, is that, and this is what Maureen discovered, is that this thing is good, or can navigate through lattices with no electronic feedback, with no sensing. It just simply does what it does, and that allows it to traverse a lattice, and in fact, even develop some interesting emergent behaviors like little spontaneous reversals to get itself out of jam. And I contrast that with some work I did with Howie Choset a few years back, in which they developed a very beautiful and complicated shape-based compliance scheme, which requires a whole lot of computation to move better through a lattice at this stage, but still applying a different scheme. And we're interested to test this on the sort of diverse locomotors we've been studying to see how changes in species and even across scales change their control scheme as they're moving through heterogeneous environments. Okay, well, this is just the tip of the iceberg with cool pterodynamic interactions. The summary is novel environmental interactions during pterodynamic self-propulsion via self-deformation. Interaction of animals, robots with heterogeneities reveals what we call, I'm calling them wavical dynamics, helps understand control scheme, and real snakes improve robots. We've studied other problems, which I'm going to flash up here. If you're interested, we're interested in how organisms and models of organisms couple strongly to environments like granule material, where they generate a kind of self-generate a fluid, which then back reacts on the organism, which then changes its properties. We've been taking this to sort of bizarre levels of looking at how robots moving on spandex membranes can actually be better described as test particles in a fiducial space-time using a general relativity description. And an outstanding former postdoc in my group, Yasmin Ozkanaiden, has taken these kind of ideas of soft and active systems and developed a fully open loop myriapod robot, which basically can almost go anywhere with no brain power. Okay, so such interactions are largely unexplored, quite rich, and hard and impossible to simulate. And if I have any big point at the end of this, it's that when I was looking up the history of this field and looking for some papers, I came across, of course, the work of Rodney Brooks. And I found these two papers. I found many papers, but I found these two papers which really spoke to me. And Brooks says here in this paper, Real Robots, Real Learning Problems, Simulating the World. Simulations are doomed to succeed. Even despite best intentions, there's a temptation to fix problems by tweaking the details of a simulation rather than the control program of the learning algorithm. Another common pitfall is the use of global information that could not possibly be available to a real robot. Further, it's often difficult to separate the issues which are intrinsic to the simulation environment from those which are based on the actual learning problem. And elephants don't play chess. There's plenty of room for experimentation. Eventually, when we are mature enough, there's also room for much theoretical development of the approaches to artificial intelligence based on the physical grounding hypothesis. And as not a plea, but as something you might be interested in the last few years, I and some others have kind of introduced a discipline, or really as integration of robotics and physics, and where we not only treat the robots as artifacts, which we might test control hypotheses on, or beautifully engineered devices, but we treat the robots as experimental tools to test hypotheses and learn from, learn new physics, learn new pterodynamic interactions. And if you're interested, you could see reviews here. And if you're really interested, every year for the last 5 years, 6 years, I should say, we've been running a focus session at the big American Physical Society March meeting on robophysics. This year, we had 55 talks and 5 sessions. And one of my panelists, Rebecca, was an invited speaker and gave an outstanding talk. And I'm really looking to mix, as somebody said this morning, I think Josie said about this interdisciplinary mix. I'm really looking to bring in engineers, computer scientists, physicists, biologists, mathematicians, etc., and to really sort of explore the beautiful phenomena that robots can teach us. So I'll close there, and thanks.
Thank you so much. And I really love your term, robophysics. And it just shows that robots aren't just for the engineers, they're for the biologists, they're for the physics. It's a way of understanding the world, isn't it? And that's just a lovely view to really sum up what this is all about. So thank you very much. So again, we'll come back to lots of very interesting questions